Good morning. Happy Monday. Thank you all for being here. Thanksgiving. Woohoo! Anyway, just as a quick reminder that the only thing we're doing this week is this lecture right here. There's no labs on Wednesday. There's nothing to turn in, stuff like that. So I hope you all have a great holiday. If you do have extra time, you want to start looking at problem set 6, of course, that would be cool, but you certainly don't have to. It's completely up to you. We're going to start off where we left off last Monday at the end, pretty close to the end of Chapter 6, Part 1. And we talked about the first of the 4 quantum numbers. And as a quick review, the first 4 get symbols N, L, and M sub L. And I'll talk about those as we go through. And this is going to be something that you're welcome to work along with me, or you can just kind of watch me as I fill in the different spaces. It's totally cool. But I'd like to show you all the values that happen when you get to n equals 3, okay? And along the way, we'll talk about the n, the l, the m sub l, and stuff like that. Now, last Monday, I talked about how the n values are kind of like a street, and l values are kind of like houses, and m sub l down here are like the number of rooms in the house. And I'll try and do analogies with these here. So you can imagine that what we're looking at here in this n equals 3 quantum thing, we're looking at the 3rd street, okay? And the first thing we're going to find out is how many houses there are, how many L values. And then we'll further break down in this house how many rooms there are, in this house how many rooms there are, and stuff like that. And along the way, you can begin to see then more about how these quantum numbers work together, what they do, and stuff like that. One more thing too before I forget. The L values have letters associated with them. So as we talked about last Monday, L values start at 0 and they go up to n minus 1. But letters that correspond go S, P, D, F, G, H, I, etc., etc. So we'll talk about those later too. A lot of times these orbitals use what's called NL notation. And N is a number, and L can be a number, but having 2 numbers next to each other, you're not sure if it's like 30 or 31 or something. So the letters just help us to figure out what the L value is that goes along with it, etc., etc. Okay. So n is what they call the principal quantum number, and it helps with the size of the orbital and also the energy. And n values start at 1, and they are whole numbers that go all the way up to infinity in theory. So we're looking here at n equals 3. We're not looking at n equals 2, n equals 1, n equals 4. N is never a fraction. It's never negative, not 0. Now, L values, though, depend on n. So if n is a whole number, blah, 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 blah. L values definitely depend on n. They always start at 0, and they're whole numbers that go up to n minus 1. So in this example, if n equals 3, L values will start at 0, and they'll go up to n minus 1, 3 minus 1, which is 2. So the L values here are going to be 0, 1, and 2, all right? It always goes up to whatever your n is minus 1. So with my cheesy example then about houses on the street, on the 3rd street there are 3 houses, and the L values of those houses are 0, 1, and 2. This down here is just kind of an overview of what I just wrote on the chalkboard. Any questions on that? Is that cool? All right. Now, as I stated earlier, sometimes we put in chemistry the n value next to the L value. And if you have 3 for n and L of 0 and you put them next to each other, it would look like 30, all right? And because n is a whole number, you could in theory have an n value of 30. So what happens a lot of times is we use these letters, the S, P, D, F, G kind of letters to go along with it. So for example, when L equals 0, that means you have an S subshell. And when L equals 1, you have a P. So these are the letters that go along with these subshells. The L values are called subshells. They represent the area mostly that the electrons hang out, the shape of the things. So we'll talk then later about a 3s and a 3p and a 3d. Those are types of subshells. And again, those are kind of the names of the houses on the street. So the 3s is one subshell, one house. 3d would be another subshell house. Any questions? Okay. So NL notation is really useful, as we'll see in this kind of stuff. And it's literally just the N number next to the letter. So 3S, 3P, and 3D would be the NL notation that goes along with it. So again, notice that N equals 3, they all have a 3 in front. But because the L value differs, that's why the letters differ for what's going on. Okay. So now we know there's 3 houses, 3S, 3P, and 3D. And some houses, as you know, are fancy and some are kind of more cheesy. So the next thing we're going to do is figure out how many M sub L values there are. And the analogy I use is that M sub L is like the number of rooms. Now, L depended on N, like the maximum L was N minus 1. M sub L values depend on L. And they always go from negative L to 0 to positive L. So there's going to be, we're going to look at these numbers right here on this first row to figure out what the allowed M sub L values are. M sub L will at least be 0, all right? That's always an allowed value. And you might have more or so and stuff depending on L. And by the way, if you have L equals 0 or M sub L equals 0, that doesn't mean it doesn't exist. That's like a legitimate address, okay? So if you see a 0, that doesn't mean it isn't there, all right? It means that it's just one of the L values or M sub L values. So when L equals 0, M sub L goes from negative 0 to positive 0. And negative 0 and positive 0 is just 0. The only M sub L value for this one is going to be 0. That's saying there's essentially one orbital. Now when L equals 1, then that's where this minus L to positive L thing comes in. So you would go minus 1 to positive 1 in whole numbers, minus 1, 0, plus 1. And when L equals 2, same idea, but now you go minus 2 to positive 2 in whole numbers, minus 2, minus 1, 0, plus 1, plus 2. So you can see as L gets bigger, the number of M sub L values get bigger, all right? Like at first there's only one value of M sub L. Then for L equals 1, there are 3 values of M sub L. And when L equals 2, you get to 5 values of M sub L. So this would be one orbital right here because we have one allowed M sub L value. In the next one over, in the 3p, we have 3 allowed M sub L values. So that would be 3 orbitals, minus 1, 0, plus 1. Those are the 3 values. And here you would have 5 orbitals because we have 5 allowed M sub L values. So notice here how there's patterns to things, like 1 to 3 to 5, all right? If L was 3 and we had a legit, the next one down there would be 7, all right? There's some quick and dirty ways to find the number of orbitals. If you have an N value only, then N squared is the quick way to find the number of orbitals. So if you add up 1 plus 3 plus 5, that's 9. That's the same thing as finding 3 squared, all right? Quantum is filled with different ways to find these patterns and stuff, and you can do it like this kind of way to figure it out, or you can sometimes just use the quick way and stuff, and either way is okay. So, on the N equals 3 street, there are 3 houses, and we'll call them 3S, 3P, and 3D. The 3s is a single room, a single orbital, okay? The 3p has 3 rooms, 3 orbitals inside it. And the 3d would have 5 rooms or 5 orbitals inside it. So like this would be a fancier house, this would be like a 1-room shack, all right, something like that. Any questions on this? Another thing that sometimes people will do is they think about these as train tracks, and this is cool too. Let's look at this one right here. This is n equals 3, which we just looked at. And on n equals 3, their L values are 0, 1, and 2. So the first separation here is for L values. And then when L equals 0, there's only M sub L equal to 0. So there's like a single track, all right? But when you get to L equals 1, the 3p, we saw there's negative 1, 0, and plus 1 for M sub L. So those are the 3 tracks for the 3p. And here are the 5 tracks, if you will, for the 3d, negative 2, negative 1, 0, plus 1, plus 2. Notice here again the pattern. It's like when n is 1, L can only be 0. So there's only M sub L equals 0. It's like a single track. All right, there's only one part. On the other hand, when n equals 2, then L can be 0 or 1 up to n minus 1. And notice here how the n equals 1 splits into 3, just like this one split into 3. So sometimes people like seeing these and these kind of patterns too, and that's fine. Any way you want to figure this out is pretty awesome. And again, just to really step back here for a second, all right, remember that all these crazy quantum numbers come from the equivalent of like Math 254, all right, the multidimensional calculus stuff. And we're using the results of this complex math to figure out ways to describe how electrons get placed around atoms, which is really pretty crazy. But anyway, it's all stuff you can do. Any questions on that? Cool. On last week, Monday, we looked at the S, P, and D orbitals. And I want to go through here real fast and just show you what the F's are. On the periodic table, we're going to see there's definitely S's, P's, D's, and F's. We don't have G's yet, but we're getting close. One of these days, a new periodic table. But anyway, we have S, P's, D's, and F's. And S, P's, and D's we'll see are very common. F's are kind of fun to talk about, but they're not as common as the other one. So if you had n equals 4, L goes from 0 up to n minus 1, so 4 minus 1 would be 3. So the L values 0, 1, 2, and 3. So this is like saying that on the 4th street, n equals 4th street, there are 4 houses, all right? Now the official word is not houses, it's subshells, all right? But same idea. There are 4 subshells on the n equals 4 shell. Or if you want, there are 4 houses on the n equals 4 street. Now, when L equals 0, that's when we get into the S subshell, all right? So for L equals 0, there's only one M sub L value. M sub L equals 0. That's like one room in this house. So the 4S subshell has a single orbital. Just like we saw on the last slide, if L equals 1, then M sub L goes from minus L to positive L in whole numbers. So minus 1, 0, plus 1. And each one of those represents one of the orbitals. So there's 3 orbitals in the 4p subshell. For L equals 2, now we have M sub L negative 2 to positive 2 in whole numbers. Negative 2, negative 1, 0, plus 1, plus 2. Excuse me. So that's the 4D subshell, and there are 5 orbitals or 5 rooms in that subshell. But the new one on this level is when L equals 3. So when n was equal to 3, the maximum L was 2. But here, when n equals 4, the maximum L now is 3. So this is the new one. And if L equals 3, M sub L, negative L to positive L, negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. And there are 1, 2, 3, 4, 5, 6, 7 allowed m sub L values, so that means 7 orbitals for the 4f subshell. And this is one we haven't seen yet, but it's the same idea as the ones we've talked about before. These are the pictures of the orbitals. We saw pictures of the S, P's, and D's last Monday. The S's were like big spheres. The P's were kind of like a figure 8. The D's were kind of like 2 figure 8s. And if you use your imagination on these, most of these look like 3 figure 8s. That's the way I always think about it myself. They're not totally that way, all right? There's some weird like donuts and stuff like that. Anyway, this is more just show and tell. It's nothing you have to worry about, but if you did a lot of types of chemistry with F orbitals, this would be the kind of thing you think about more often than not. So I just wanted to show you pictures of them. It sometimes is difficult to find pictures of the F orbitals, but again, this is where the electron is more than 90% of the time, all right? So more than 90% of the time it's in like one of these globes if it's in this orbital, all right? And that doesn't mean it's there all the time, and we have to make a choice if we know energy or position. We always choose energy, so that's why we have these pictures to show where the position of the electron is more than 90% of the time. So after this, oh, go ahead, Wes. Yeah.
I'm just wondering about like what the color represents.
Right.
Is it just to show it's different somehow?
That's a really cool question. So these are all based on waves, okay? And in a normal like sine or cosine wave, there's like an area above the 0 and an area below the 0. And so sometimes they'll label those as like positive, negative. And these things here, Wes, are kind of like positives versus negatives, all right? Yeah. And it has to do more with the math and stuff like that, but it can make a difference in helping to predict like where the electrons are. And we'll see in the next chapter that you can have 2 electrons in each one of these. And so you can think about it, Wes, as like one electron would be in the blue mostly, and one would be mostly in the yellow. Right on. That's a cool observation. Yeah, the colors are intentional just to show the difference in the positive or the negative part of the wave, if you will. Great question. That was a cool question. Okay. This chapter is kind of different compared to some of the other chapters. So I tried to make this list of things that I think will help you as you study for it, as you go through problem set 6 and stuff like that. The first 2 things are these 2 constants, which are very helpful. The first one is the speed of light, 2.998 times 10 to the 8th meters per second. Also, the other one, h here, is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And these are both used a lot, and they're used in these equations right here mostly. We saw that the energy of a photon is proportional to the frequency. That little nu right there is the frequency symbol, and it's proportional based on Planck's constant. And we also talked about how frequency and wavelength, this number, equal the speed of light. So what sometimes people will do is they'll substitute in for frequency speed of light over wavelength. And if you do that, this is the equation you get. So these ones right here are what we use a lot. It relates the energy to the frequency, the nu, as well as the wavelength lambda. And if you have one, you can calculate the other, no problem. Remember, frequency is like the number of waves per second or cycles per second, and it's usually given the symbol hertz. A hertz is just equal to 1 over a second. Now, because electrons and photons sometimes behave like particles and sometimes they behave like waves, this equation is also really important, and this is de Broglie's equation. And de Broglie said that objects with mass m and a velocity, speed, meters per second, will have a wavelength associated with them. And when it comes to electrons, this is really important. because all the pictures I showed you of the f orbitals that Wes asked about and stuff like that, those are really pictures of waves. They're standing waves around atoms, all right, around the nucleus of an atom. So we think of those electrons as literally having a wavelength, all right? They're like waves, man. And de Broglie's equation that helps us to understand the wave-particle duality, which is just a fancy way for saying how sometimes these things act as particles and sometimes they act as waves. And it's really only appropriate for electrons and photons, those small, fast things and stuff. The number of orbitals will be something I'll ask you about in problem set 6. Quickly, the number of orbitals in a shell is equal to n squared. So we saw how for n equals 3, there were 3 squared 9 orbitals. If you have a subshell, if you have an L value, the number of orbitals is 2L plus 1. So for example, when L equals 1, the p subshell, then 2 times 1 plus 1, 3 orbitals are in the p subshell. So these are kind of quick and dirty ways to not have to think as hard about the m sub L values. To talk about the subshells and also their energies, we use the n values and the L values. And these letters are super helpful, like we'll see in the next section. So we've already talked about 3s, 3p, 3d. SP and D refer to the L values, all right? So you can quickly tell then what the L value is. So for 4D, N would be 4, L would be 2, all right? For 4P, N would be 4, and L would be 1. And then finally, last week, Monday, we talked about nodes, which are areas where there's no electron density. And when you start making molecules, they have to stick together. They have to have electron density on them. So there are planar nodes, which are basically planes of glass that go through the orbitals, and there's no electron density there. Planar nodes are just equal to L. So if you have a 4D subshell, D means L equals 2, it would have 2 planar nodes, all right? On the other hand, if you had a 4P, then P has L equals 1, there would be 1 planar node. But if that wasn't enough, there's also what they call spherical nodes, which are basically like balls within balls, all right? And on the inside ball, that's an area where there's no electron density. And you can figure those out quickly if you know N and L. N minus L minus 1 is how you do it. So 4D, again, has N equals 4, L equals 2. The number of spherical nodes, 4 minus 2 minus 1, there would be 1 spherical node. If you've got these things down, then this chapter will fall for you. It's a little weird, I won't deny, and we'll go over more in problem set 6 and stuff, but any questions? Okay. I want to talk about, show you a video real fast about why the nodes are important. And this is more of a Chem 222 thing, but I want to show it to you anyway, just to see how certain configurations can be predicted, while other predictions we'd say will never happen.
Isosalt is a compound made from platinum chloride and ethylene. The ethylene cannot bond to the platinum unless orbitals in the 2 fragments are oriented properly to each other. This alignment occurs most effectively when the ethylene is perpendicular to the molecular plane of the platinum chloride fragment.
So for this molecule, that ethylene, which is that thing on the right, you could have it perpendicular or you could have it parallel. And only the one configuration is seen because of the orbitals, all right? There aren't enough orbitals in the other direction, so you always see this version and not the other one. And believe it or not, that's a big thing in chemistry because the reactivity would be quite different probably if it was up and down versus left and right, all right? So this is where the nodes can be really helpful to figure out and stuff and figure out how the bonding happens. Any questions on that? All right. So that's it for chapter 6, part 1, which I think of as an introduction to N, L, and M sub L, and also just telling you where all these things like come from, where Planck's constant, speed of light, and stuff like that. If Chapter 6, Part 1 was a little strange for you, I'm hoping that Chapter 6, Part 2 brings it back to Earth, all right? Because we're really going to see why the periodic table is written like it is right now. Like why there's gaps in the middle, why the left and the right ones are here, and the other main groups are over there, and also why the lanthanides and actinides are at the bottom. So again, if last chapter was a little strange and stuff, then hopefully this chapter will start to bring it back. And in order to do that, we need to remember that there's shells, subshells, and orbitals, which we just went through. The shells are the N, the subshells are the L, and the orbitals are the M sub L. And L depends on N, M sub L depends on L, etc., etc. But there's one more quantum number that I haven't brought up yet. And this one says that basically each of those orbitals, each of those M sub L's, can only have 2 electrons. And when Wes asked about the color of those little pictures I showed, each of those was an orbital, one of the F orbitals. And there was blue and green. And you can think about it like one electron could only be in the blue parts, and the other electron could only be in the green part. So this fourth quantum number is given the symbol M sub s. And the very fact that they found M sub s is just amazing. So Schrodinger came out with quantum mechanics, blah, blah, blah. But in the original version of quantum mechanics, there were only N, L, and M sub L. Well, this guy, Paul Dirac, going crazy with the math, but anyway, he applied Einstein's relativity, which is another big field, to quantum mechanics. And when he did that, this M sub s value came out naturally. I find that just fascinating because already quantum mechanics is pretty complicated, and he added even more math, and bam, M sub s pops out, and that's really, really cool for chemists. So M sub s was kind of a late bloomer, if you will, but it's super important because it basically says that each of these rooms in a house can only hold 2 electrons. So of course I have to use the analogy then of how if in a room you could in theory have 2 people per room. Like if you lived, when you grew up maybe, you had a brother or a sister, and if you have to, you could be in the same room with them. But it's nicer to have your own room, all right? You can have your own posters up and play your own music, whatever, all right? But if you have to, you can both be in the same room. And electrons follow that too, all right? Electrons prefer to be on their own, in their own room, in their own orbital, but if they have to, they can be paired up as well. And that's the kind of stuff we're going to talk about. And again, it's all due to this guy here, Dirac, which is pretty crazy. So, the fourth quantum number is M sub s. I'll put it right here, and it's called the spin quantum number. I hear you. Okay, I like really bad horror, and this is from House of a Thousand Corpses. And anyway, if by this point you're like, "Oh, Russell, what are you doing, man? Quantum, blah blah blah, relativity, man." Well, it probably sounds at first like, but trust me, it's gonna start coming to fruition here pretty soon. So just hang tight, and it gives me a chance to remember that really cheesy movie that I like. Anyway.
Any spinning electric charge creates a magnetic field. Spinning electrons produce magnetic fields with an identifiable magnetic polar orientation, so-called north or south. The polar orientation of a given electron is determined by the direction of its spin.
Now, M sub s, the analogy of what it means, all right, is that electrons are constantly spinning, all right? And electrons spinning create a little bit of a magnetic field. And if you have an external magnet, all right, like another atom, or actually a physical magnet, then the electrons can spin in the direction of the external magnet, or a little extra energy, they can spin in the opposite direction. So it would be, I guess, like this. So my left hand here is, I should do this in front of the camera. My left hand here is some kind of external magnet. Could be another atom, could be a piece of iron, who knows. So electrons spinning with the magnetic field in the same direction, that would be one value. But electrons could be, with a little extra energy, forced to spin opposite the magnetic field. So when we have M sub s values, there's only 2 values, positive or negative 1/2. And positive 1/2 means that the electron is spinning in the same direction as your external magnetic field. On the other hand, if you have an m sub s, which is minus 1/2, then that means it's going against the external magnetic field. It's not a huge energy difference between those two. It's like 10 to the minus 18th joules or something. It's pretty small. However, usually you want to put things in the positive 1/2, spin up the up electron, left up arrows, we'll see in a little bit first, because it is a little bit easier, less energy than the negative minus 1/2 value. So we saw that L depends on N and M sub L depends on L. M sub S positive or negative 1/2 only, and no dependence on any other of the quantum magnetic numbers. Any questions on that? So this leads to magnetism, and this is going to be a zero-level introduction to what magnetism is. Electrons spinning create a little bit of a magnet. Most materials, these arrows represent the spins. Most materials have just as many up arrows as they have down arrows, and we refer to these as diamagnetic systems. Diamagnetic systems are just no magnetic field. There's no net magnetism going on. And that only happens if you have just as many up arrows as you have down arrows. And most of the things that we deal with in our day-to-day life are diamagnetic. They're not magnetic. However, it is possible, and we'll see examples of this, how you have more up or down arrows. You have some kind of net excess arrow direction going on, all right? And that means that it's what's called paramagnetic. And paramagnets are just more ups arrows than downs, or more downs than up, doesn't really matter. But you do have a net magnetic moment. And these will create then a little bit of magnetism, and that has an effect on the reactivity we're going to see. So you can think about it as diamagnetic, no magnetic field, just as many ups as downs. Paramagnetic, though, you will have some kind of net more up than down or more down than up, some kind of magnetic moment. These aren't super strong magnets by any means, but it is something that does affect their reactivity. Now, if you've ever been to OMSI, though, and you play with some of their super magnets, those are pretty wild. Those are like super paramagnetic things. And super paramagnetic things are different than regular paramagnetics. So if you have a paramagnetic substance and you apply an external field and you're able to get them to all align, this is what makes a ferromagnetic substance. A ferromagnetic substance is like supercharged paramagnetism, all right? Instead of having all the ups and downs, left, right, up, down, stuff like that, all of a sudden they're all aligned like troops in an army or something like that. And if they're all aligned, that makes for a very, very strong magnetism. So if you've ever played with a magnet, a true magnet, those are ferromagnetic. They're not just paramagnetic, but it's like every one of those individual paramagnetics all aligned in the same direction. So you have a really strong substance. Certain elements are definitely able to make ferromagnetic materials easier than others. In theory, any paramagnetic substance could be made into ferromagnetism, but that's pretty unlikely. It's only for a couple of them that you actually see it. Cool. A ferromagnet, when the external field is removed, you actually then keep the orientation, and that's pretty cool. Most paramagnetic substances, if you take away the field, then they just go back to being random and stuff. But the ferromagnetics, they keep their magnetism for a long time. So diamagnetic systems don't have any magnetism. And it's not that they don't have it, but you have just as many up electrons as down. In a paramagnetic system, you do have a net increase, more ups than downs or more downs than ups, but they're not super strong. And these ferromagnetics are just like super magnets. They stay on once they're done. You can take away the external field and they still have their orientation. Wes, you had a question?
Yeah, about the permanent magnets, is there any way to undo that by applying power?
Yeah. I have heard there's certainly some chemical ways, like if you don't mind destroying the magnet, you can absolutely take away their magnetism and stuff like that. However, in terms of a physical process, I can't help but think that there would be some way, like maybe if you had a magnetic field in the opposite direction, maybe you could nullify them. But honestly, I'm not sure, Wes. I'll be honest. That's a good question. I'll have to think about that a little bit. Other questions? Okay.
Different materials have different magnetic properties. Liquid nitrogen is diamagnetic and is not attracted to the magnet. Liquid oxygen is paramagnetic. Paramagnetic substances in the liquid or solid state are generally attracted to magnetic fields. Liquid oxygen is held by the magnetic field.
So this is the difference between a diamagnetic and a paramagnetic substance. Liquid nitrogen, we'll see next term, is diamagnetic. And so what happened when you put the liquid nitrogen through this magnet, it just went right through. All right, didn't stick around the magnetic poles at all. And all diamagnetic systems, I would argue, at least at these temperatures, would go through with no problem. But paramagnetic substances stick, if you will, between the magnet heads. And we'll see next term as well that liquid oxygen is actually a paramagnetic species. So when you pour the liquid oxygen, which looks just like liquid nitrogen, looks just like water, liquid oxygen actually sticks between the magnet heads. The little paramagnets, those odd electrons, will stick, if you will, to the magnetic heads in between and kind of do some unusual things. And again, the only way you're going to have paramagnetic things is if you have unpaired electrons. So one of the things we'll learn about in the system is how to tell if carbon has unpaired electrons or neon or something like that. And it's not too difficult. There's actually a lot more paramagnetic substances out there than you might think. Any questions on that? Okay. You can measure how paramagnetic something is. This is like just a protractor, and they put a little line on it with a weight on the end, all right? And if the substance down there is magnetic and you put an external field to it, the magnet will actually shift a little bit. If you do it with a better weighing system, it actually pulls down into the magnetic system. So the amount of paramagnetism in here is proportional to the pull, which you can feel in a weight and stuff. I had a student a few years ago that went to Portland State, and she did physics research, but in her physics research, she was actually measuring the number of unpaired electrons with a system like this. I thought that was pretty cool. So there are ways to measure like how paramagnetic something is and stuff. You can just do it yourself, but you can also have elaborate equipment set up. So. Okay, so the quantum numbers again, and the shell number, whole numbers starting at 1, going up in theory to infinity. L has a dependence on n, so if you know n, L always starts at 0, and it goes up to n minus 1. So when we saw n equals 3 earlier, L goes up to 3 minus 1 or 2, L values 0, 1, and 2. M sub L depends on L. You have to know L to know what M sub L values are. So for example, when L equals 1, M sub L minus 1 to positive 1 in whole numbers. So minus 1, 0, plus 1. But if L equals 2, then M sub L minus 2 to positive 2, minus 2, minus 1, 0, plus 1, plus 2. The orbitals increase as L increases. And then the new player on the block here is M sub S, electron spin. M sub S doesn't depend on anything else. M sub S is only positive 1/2 or negative 1/2. And again, you can think about it like positive 1/2 as being with the external field, negative 1/2 being against the external field. Okay? So now that we know these, we can start putting things together to see how electrons are placed around atoms in the nucleus, which is pretty interesting. So here's a question we talked about a little bit on last Monday, about which is not a valid set of quantum numbers. So we use the rules. This is a common kind of thing when you're learning the quantum numbers to see which one is not legit. So for example, on the first one, n equals 4. Well, as long as n is a whole number, you're good to go. It has to be 1 or larger. These are all whole numbers. They're not 0 or negative or something like that. L can be no bigger than n minus 1, and it has to be 0 or higher. So like for L equals 1 and n equals 4, then that means L could go up to 3, up to n minus 1. So that's legit. M sub L numbers have to go between positive L and negative L. So if L equals 1, M sub L could be negative 1 to positive 1, negative 1, 0, plus 1, so that's okay. And the new player on the block, of course, is M sub S, and M sub S can only be positive or negative 1/2. So it's probably not too hard to see that this one right here is the bad one, because M sub S is never 0, all right? M sub S is only positive or negative 1/2, all right? The other ones here all work out fine. It's just the M sub S is only positive or negative 1/2. Any questions on that? So Pauli, Wolfgang Pauli, is another player in the quantum world. And he came out with the idea that every electron in an atom has to have its own set of quantum numbers. And they call this now the Pauli Exclusion Principle, named after him, all right? And I use the idea that if these are electrons, like people, and I wanted to send an invitation to my party, all right? I wanted to send it to Ben, but not Nick. No offense, Nick. I totally would send you an invitation to my party if I had one. But let's say I wanted to invite just Ben and not Nick. Well, I would need his address, all right? And Nick and Ben might actually live at the same house, but if I put, Ben's name and which room he's in, then the post office could deliver him the invitation and not Nick. And again, Nick, I would absolutely invite you, so this is a silly example. But that's kind of how electrons are in atoms. Like maybe we want to send an invitation to the third electron, but not the fifth electron, all right? That's what the Pauli exclusion is all about. And if each electron has its own set of 4 quantum numbers, we can do that. We can send the Ben electron an invitation, but not the Nick electron, or vice versa, right? So the N, L, M sub L, and M sub S values we've been going over them for a reason, because now we're going to start assigning the electrons, each one of them, a certain number of quantum numbers. And each electron in the atom is going to have its own set. Now, let's just do a quick review on a periodic table here. The blue numbers on the periodic table, the atomic numbers, really represent the number of protons. But in a neutral atom, the protons and the electrons will be the same. So for hydrogen, there's only 1 electron. Helium, there's 2. Lithium, there's 3, etc., etc. But man, you get down to like gold, 79 electrons. So we're going to have lots of different quantum numbers running around for these things, because each electron is going to have its own address, all right? And that's where these different quantum numbers come in. So we'll look at some examples here of how you'd assign these quantum numbers to electrons in different atoms. Any questions on that? Sweet. Okay, so let's go back to when n equals 1, all right? So when n equals 1, L values go from 0 up to n minus 1. 1 minus 1 is 0, so only one L value, L of 0. And M sub L minus L to positive L minus 0 to positive 0, only 1, 0. So in the 1s subshell, remember L equals 0, that's an S. In the 1s subshell, there's only 1 orbital, only 1 M sub L value, all right? So these sets right here are the N, L, and M sub L. Now, M sub S, remember, can be positive 1/2 or negative 1/2. So in this single orbital, we can assign 2 sets of quantum numbers. They both are n equals 1, L equals 0, and L M sub L equals 0. That's the 1s orbital. But now we can put on M sub S. So M sub S can be positive 1/2 or negative 1/2, all right? And what we've just done there is assigned four quantum numbers to each of those electrons. They're the same except for m sub s. Now, earlier I said how electrons are like people, and you could, if you want, have like a room in your house and be with your brother or your sister or whatever, all right? If you have to. This is like saying you're living on n equals 1 street in the L equals 0 house, and there's only one room, one m sub L value, but you're both there. This is you positive 1/2, and this is your brother or sister ms minus 1/2. That's kind of what it's saying. There's 2 people per room, all right? And the 2 people come from the 2 m sub s values. Each m sub L value, each orbital value, is going to hold 2 electrons, 2 people, because of this m sub s part. So these 2 electrons then have their own set of quantum numbers, all right? The last m sub s is enough to make them different from each other. And in the chemistry world, this would be like the address of the first electron, and this would be the address of the second electron. So if I want to invite this electron to my party, I'd send it to this address, but if I don't want this electron to be invited, I wouldn't send one to that address. Okay. Now, when n equals 2, the second street, now L values, the subshell, the number of houses, starts at 0, goes up to n minus 1, so 0 and 1. So this street is going to have a 2s and a 2p house, okay? Now, in the s house, when L equals 0, m sub L will also be 0. M sub L depends on L. So in the 2s house, these parts right here, notice the similarity to what we have up here, all right? N equals 2, L equals 0 for this particular subshell or house. Only one room in the L equals 0 house, one m sub L value, and you can have positive or negative 1/2. So these are the quantum numbers for the 2s subshell, all right, for the 2s subshell. And it has one orbital. Now, this is a fancier house. Woohoo! It has 3 rooms, 3 m sub L values. The negative ones, the zeros, and the positive ones. The negative 1 room can hold 2 people, positive 1/2, negative 1/2. The m sub L equals 0 room can hold 2 electrons. The m sub L positive 1, 2 electrons. 6 possible electrons in the 2p subshell. And notice here how all of these sets of combinations are different, all right? There's no n equals 1, L equals 0, m sub L equals 0, m sub L positive 1/2 anywhere else except right here, okay? And that's what Pauli was implying then, how each electron has its own set of 4 quantum numbers. You're changing here the n. You have 2 types of subshells, S and P. The p subshell has 3 orbitals, 3 m sub L values, so that's why you have more numbers. Yeah.
Earlier we had the diagram of the railroad tracks.
Right.
So are we saying that for each railroad track it can hold 2 electrons?
Cool. The railroad tracks, Wes, were the subshells, the orbitals, all right? So like in that diagram for n equals 2, there was a single one that went off, and the other one split into 3, okay? So the single one that went off, all right, was when m sub L equals 0. So both of these together are on that single track, all right? Then there's 2 negative 1s, 2 zeros, and 2 positive 1s. Each one of those pairs would go through one of the 3 parts right there. So in the train diagram, you're not seeing the individual m sub s, but you are seeing the orbitals, the m sub L values, yeah. So that would be the way to extend it then on there. Each one of those tracks, the final tracks, would hold 2 electrons. You'd have like a up and a down electron. Okay. Excellent question, once again. Yeah.
Will the L's be given? I guess I'm just confused on how you decided on 2s and 2p.
Cool. So if you know n, all right, then L always starts at 0, and it goes up to n minus 1. Yeah, it's a good question, man. So like if you had n equals 4, then L would go from 0 up to 4 minus 1, 3. So you'd have 0, 1, 2, and 3. You'd have 4 L values. That's right. That's a good question, man. That took me a while to figure out myself when I was learning this, so I'm glad you asked, man. So yeah. Other questions? Okay. So these are the sets of quantum numbers for n equals 1. This diagram right here is a set of quantum numbers when n equals 2. These get kind of crazy, all right, but they're just more and more sets of quantum numbers. All of these are n equals 3. So this is where we started this lecture this morning. We had the n equals 3. And Ben, going back to your question, if n equals 3, then L starts at 0, and it goes up to n minus 1, 3 minus 1, 2. Okay? So here's L equals 1, L equals 0, L equals 1, and then L equals 2. And notice the letters. All right, L equals 0 is S, and this is 3S for that reason. 3P, 3D, and stuff. But again, the quantum numbers just keep on coming, all right? Each of these orbitals has 2 m sub s values. And again, that represents the fact that each of those little rooms can have 2 electrons, one spin up and one spin down, all right? So you start getting into more and more different pieces. This is the total number of electrons. Notice here how the s orbital holds 2 electrons. The p's have 1, 2, 3, 4, 5, 6 electrons inside them. The patterns, notice the patterns, 2 plus 4 is 6, 6 plus 4, 10 electrons in the d. So the total number of electrons in the n equals 3 shell is 18, 10 plus 6 plus 2. We saw earlier that the number of orbitals on a shell was n squared, 3 squared, 9. And again, that came from 5 plus 3 plus the 1, 3s. So if n squared is the orbitals, then 2n squared would be the number of electrons. So again, n squared, 3 squared, 9 is orbitals. Well, 9 times 2, 18 electrons. Quantum mechanics is filled with these patterns. You know, people that do numerology are probably freaking out in this stuff. But anyway, just trust in the math, man. It is all based on math when it comes right down to it. Questions? Okay, I'm just going to show you this just to show you. This one I had to have 2 columns because it was going on so crazy. This is the n equals 4 shell. Now n equals 4 means L goes from 0 up to n minus 1, 3. So that would be 0, 1, 2, and 3. And the letters that correspond with that would be S, P, D, F. So you can see here's 4S, 4P, 4D, and now over here, 4Fs. So the pictures that Wes asked about with the blue and the green and stuff, those pictures are these orbitals. So I don't know which one was this particular 4F, but the 2 electrons, like one would be like in the blue part, and the other one would be in the green part, something like that. And you can just see, just keep plugging them in. So this part then just talks about then how all the electrons have their own set of quantum numbers, and that's what Pauli exclusion is all about. You wouldn't want to have 2 electrons with the same 4 set of quantum numbers. You have to change at least one of them, usually m sub s, but whatever. You can't have them have the same. It has to do with energy, we'll see. It also has to do, you can think about it like if you wanted to send a letter to this electron, but not that electron. You need a slightly different designation to tell which one it is. Questions? This is just kind of a summary of the different things we've seen here so far. So here's n equals 1, 2, 3, 4, etc., etc. Number of subshells. So remember, if n is 1, L starts at 0 and goes up to n minus 1. So there's only S here, but there would be S and P for L equals 2, 0 and 1. For 3, like we've seen, 0, 1, and 2 would be SPD. SPDF, et cetera, et cetera. Now, eventually, you start getting into some that haven't been found yet. They have little stars next to it, and I'll talk about that. In the chemistry world, we are very close to a 5G orbital. Not quite there yet, but I'd love to have it. I'd love to show all the G orbitals up here, but this is my chemistry fantasy, obviously getting a little crazy, but anyway, just realize the ones with the stars, it's room for improvement, all right? You're out in space and you find some kind of heavy element, well, we've got the room and stuff all set up for it. Here at the top, notice the number of electrons, maximum electrons, 2 times n squared. So 1 squared times 2, 2 electrons. 2 squared 4 times 2, 8 electrons, etc., etc. Number of orbitals, blah, blah, blah. It's all coming together. Any questions? Yeah.
So n equals 5 doesn't exist.
So n equals 5, the ones with the stars don't exist. So we're going to see here in a little bit that 5s, 5p, 5d, and 5f totally exist. We've got them right now. But we haven't got to the 5G part yet. So it's like we've only seen some of the houses, Jonah, on the n equals 5 street. We haven't seen them all. So we haven't seen 5G, and we haven't seen some of these 6s down here, but we've actually seen some 7s, even too. This isn't a complete list. It just kind of depends where you are on the periodic table. And we'll talk about this and stuff here. Okay, this is going to be a good place to take a break. It's 9:55, so take a 5-minute or so break. We'll meet back here around 10 o'clock.